The inner solar system is alive again. An orchestra of volatile ice and solar radiation, a glowing ballet of ionized gas and dust reflecting the furious light of the sun. As Earth spins through October skies, 4 comets are awakening in tandem, each one shaped by the same ancient physics that once governed the birth of our solar system, each revealing, in their expanding comae and trailing tails, the fingerprints of the forces sculpting interstellar matter. Comet 3IATLAS, the interstellar visitor whose orbital trajectory cuts through our planetary plane at hyperbolic speed, is now stirring once again behind the sun. Its nucleus, a frozen remnant of a system not our own, is being sculpted, reshaped, and partially vaporized by the relentless energy of the heliosphere. Yet, in this unseen region, hidden by the solar glare, the comet's coma grows, jets ignite, and the dynamic plasma envelope expands under the bombardment of solar wind particles and coronal mass ejections. At the same time, Lemmon, SWAN, and ATLAS K1s, all native denizens of our own Oort cloud, are brightening, expanding, and changing form. Together, they transform our night sky into a transient laboratory of solar system physics. What astronomers now describe as growing larger is not just a brightening in visual magnitude or a widening halo of reflected sunlight. It is a complex dance of gas dynamics and solid state sublimation, where volatile ices trapped beneath dark crusts erupt through jets that vent carbon monoxide, carbon dioxide, and water vapor into the vacuum. Those outflows drag fine dust with them, silicate and carbonaceous grains that scatter sunlight and produce the dusty comae and long, graceful tails we recognize as comets. Each nucleus is a microcosm of thermodynamics and chemistry, a porous body, rotating, venting, fragmenting, a natural spacecraft shaped by physics billions of years old. 3IATLAS, the interstellar object, remains the most enigmatic, discovered with a trajectory that cannot be bound by the sun's gravity. It entered our system from interstellar space, following a hyperbolic orbit, its eccentricity greater than 1. A visitor, not a resident. Its behavior has puzzled scientists since its first detection. Unlike typical comets that display predictable phases of brightening as they approach perihelion 3IATLAS exhibited erratic outbursts, asymmetrical tail structures, and a coma dominated by XOL emissions over H/O, a ratio far higher than any native comet known to the solar family. Now, even as it remains obscured by the solar glare, instruments aboard solar observatories detect hints of its renewed activity. Not directly, but through subtle fluctuations in solar wind backscatter and forward, scattered light in coronagraph data. When we say, it's growing larger, we're witnessing the expansion of a plasma cocoon, driven by 2 opposing forces, internal sublimation and external pressure. As sunlight penetrates the comet's nucleus, layers of volatile material begin to sublimate. That outflow expands into the vacuum, creating an atmosphere, a temporary, fragile shell of gas and dust surrounding the comet's solid core. This is the coma. Beyond it, charged particles interact with the solar wind, electrons and protons streaming outward from the sun at hundreds of kilometers per second. Those charged particles ionize neutral molecules in the coma, stripping electrons and forming a tail of glowing plasma that always points directly away from the sun, regardless of the comet's motion. Meanwhile, heavier dust particles, less influenced by the solar wind, trail behind the nucleus, forming the dust tail that curves gracefully along the comet's orbital path. The interplay of these 2 processes, ionization and radiation pressure, gives each comet its unique visual geometry. Lemmon's tail, for instance, displays a smooth curvature that betrays the gradual influence of solar radiation pressure over time, while Sabion's tail is narrow, filamentary, and dynamic, often disrupted by solar wind gusts. ATLAS Quan, in contrast, shows evidence of strong dust jets, suggesting localized venting on a rotating nucleus, each vent turning toward and away from the sun, producing a pulsing, spiraling plume pattern that evolves hour by hour. But none of them behave like 3IATLAS. Being interstellar, its chemistry tells us about a different birthplace, a different stellar nursery. Its high-cal, to H-No ratio and trace metals suggest formation in an environment where temperatures remain too low for water to dominate ice formation. The result, a body rich in volatile carbon species, reactive when exposed to the sun's warmth, producing asymmetric jets and a bluish plasma tail with unusual ionization profiles. Some researchers hypothesize the presence of nickel without accompanying iron, a pattern observed in certain comets that have undergone unique formation pathways or cosmic ray exposure over millions of years of interstellar travel. When a comet activates, it is not a simple process of melting. It is a thermodynamic feedback loop. Sunlight penetrates dark, carbon-rich crust, heating subsurface ices. As these ices vaporize, gas pressure builds up, eventually fracturing the crust, releasing jets that vent at supersonic speeds. Those jets carry dust grains upward. As they exit into the coma, the grains decouple from the gas flow and continue on ballistic trajectories, forming visible halos of scattered light. If the comet rotates, those jets produce corkscrew-like trails, and as the rotation axis precesses under asymmetric mass loss, the comet's orientation changes, altering the tail geometry. All these mechanisms, unfolding together, are what astrophysicists refer to when describing a growing coma or expanding tail. Meanwhile, but the inner heliosphere is more active than usual. The Sun is approaching solar maximum, with frequent coronal mass ejections, CMEs, and high-speed solar wind streams. These interact with cometary atmospheres, compressing or elongating ion tails, and sometimes inducing what observers call disconnection events, sudden breaks in the plasma tail as magnetic reconnection severs the ion flow. SWAN, being currently within reach of solar wind monitors, exhibits such disconnections regularly, recorded by spacecraft like Satio and Stereo as rapid morphological shifts. ATLAS K1, moving through denser solar wind regions, shows bright knots, evidence of shock interactions between the solar wind and the comet's induced magnetosphere. As sunlight pressure fluctuates with solar activity, the dust tails of Lemmon and ATLAS respond with visible variations in brightness. Fine dust grains, less than a micron across, scatter blue light more efficiently, while larger grains scatter red and infrared wavelengths. Observers on Earth see these changes as subtle shifts in color and brightness, often misinterpreted as intrinsic changes in the comet's output, when they are in fact effects of solar scattering and phase angle. In photography terms, it's the cosmic equivalent of changing light direction during a photo shoot. The same object, illuminated differently, telling a different story. For amateur astronomers, the current alignment presents both a challenge and an opportunity. Lemmon, the most easily visible, is now a binocular showpiece, a faint, soft glow in the early morning sky, its coma expanding as it approaches perihelion. SWAN and ATLAS K1C are fainter, demanding long exposures and stable tracking for astrophotography. 3IATLAS, still hidden behind the Sun, remains beyond visual reach for now, but once it emerges, stacked long exposures and narrowband filters will reveal its unique spectrum. Astrophotographers will need to compensate for its rapid motion, as its hyperbolic trajectory means it moves faster than typical comets across the sky, producing elongated streaks in untracked images. To capture its structure, one must align on the comet itself, not the background stars. As these comets evolve, astronomers rely on ephemerades, precise tables of celestial coordinates predicting where each comet will be at a given time. These are continuously refined using astrometric observations from both professional and amateur astronomers. The data feed into orbit models that calculate not only position, but velocity, solar distance, and phase angle, enabling accurate predictions of tail orientation and visibility. Those who prefer facts over hype understand that each image captured from Earth is not just art, but data, each pixel, a record of photons that have traveled millions of kilometers through plasma, dust, and magnetic turbulence before reaching the telescope sensor. 3IATLAS, in particular, challenges traditional comet modeling because of its unbound orbit and interstellar origin. Its velocity vector, inclination, and non-gravitational accelerations, possibly driven by asymmetric outgassing, require advanced modeling to predict its post-perihelion trajectory. If its activity increases during solar conjunction, it could display a significant anti-tail, a forward-pointing dust structure, produced when Earth's line of sight aligns with the comet's orbital plane, causing dust particles released earlier to appear ahead of the nucleus. This optical illusion is not uncommon. It was famously seen in comets like Narrated, Roland and Weiss, where the geometry between the comet, Earth, and the Sun created visually stunning forward dust projections. The buzz in the inner solar system, therefore, is more than just aesthetic excitement. It is the manifestation of astrophysical forces at work in real time. The Sun's radiation sculpting matter, the solar wind tracing invisible field lines through the void, and small, icy bodies responding with thermochemical vigor. Each comet becomes a sensor, a probe, recording the interplay between energy and matter across astronomical distances. Lemmon's coma expansion rates provide clues about its subsurface ice composition. The ratio of water ice to carbon-bearing volatiles determines how rapidly the coma density increases with solar proximity. SWAN's ion tail offers real-time data about solar wind velocity and direction, its oscillations mapping magnetic field variations. 3IATLAS, with its dust jets and asymmetric coma, offers insight into nucleus morphology and rotation. Perhaps a fractured, tumbling body venting through multiple fissures. And 3IATLAS, the interstellar wanderer, offers a glimpse into chemistry born around another star, perhaps one long extinguished. As these comets pass through the inner solar system, they also seeded minute particles of dust and volatile organics, released from their nuclei, become part of the zodiacal dust cloud, drifting for centuries, interacting with planetary magnetospheres, and occasionally entering Earth's atmosphere as meteoric dust. Each grain carries isotopic fingerprints that trace its origins. Some will show carbon isotopic ratios that differ from Earth's. Subtle reminders that not all matter within our sky is native. When 3IATLAS finally clears the Sun's glare, likely in late October or early November, telescopes around the world will turn toward it. Professional observatories will monitor its spectra, measuring molecular bands of CN, CO, and CO to determine composition and outgassing rates. Amateurs, with long focal length optics and cooled sensors, will attempt to capture its tail geometry. Perhaps a bifurcated structure, perhaps an anti-tail, perhaps something entirely unexpected. Its trajectory will carry it outward again, past Earth's orbit, toward the outer solar system, fading over months into the background of stars. But its brief passage will leave behind data, photons and spectra, orbits and models, that deepen our understanding of how interstellar material behaves under solar influence. This is why these weeks matter, not for spectacle, but for science. The 4 comets, each governed by the same universal laws, reveal the subtle interplay of heat, radiation, magnetism, and chemistry that drives our cosmic neighborhood. When we watch Lemmon's soft green coma in binoculars, or stack CCD frames of ATLAS Equa-1, we're not just looking at frozen relics. We are witnessing energy exchange across astronomical units. The next phase of observation will involve comparing coma expansion rates to heliospheric conditions. As solar wind density increases during CME outbursts, ion tails should respond within hours, exhibiting kinks or brightness waves. By timing these changes and correlating them with solar data, scientists can map the flow of solar particles across space, turning comets into dynamic tracers of the solar wind's invisible architecture. 3IATLAS, though farther and more elusive, may display even more dramatic effects, as its high velocity relative to the solar wind could create a bow shock. A compressed magnetic boundary ahead of the nucleus, where plasma flow is deflected. Detecting this would require coordinated observations with solar observatories and ground-based instruments, but the reward would be unprecedented. Direct evidence of an interstellar object interacting with the heliosphere. For those watching the sky, the experience is both scientific and spiritual. Through a telescope, a comet is not merely an object, it is an event. Light scattered by dust grains born from frozen matter older than the Earth, transformed by heat and wind from the star that sustains us. Each observation, whether a long exposure image or a fleeting visual glimpse, connects us to cosmic time. A reminder that the same processes shaping these visitors once shaped our world and will continue long after their faint tails fade into the black. So, when you hear that, the inner solar system is buzzing. Understand that this is no exaggeration. It is a moment when celestial mechanics, plasma physics, and cosmic chemistry converge in real time. The comae are expanding, tail stretching, not as static beauty, but as equations in motion, expressions of the energy balance between sunlight, ice, and dust. Watch the breakdowns, read the ephemerides, and, above all, look up. The sky is not still, it is alive, whispering through light and motion, telling stories that began among the stars.